All right, I welcome you back to my YouTube channel. This is Mr. Hyper, and I'm taking you through chemistry. We are continuing with our topic of the chemical kinetics, and today we are going to look at the factors that affect the rate of a chemical reaction. Factors which affect the rate of chemical reaction. Before we start, I want you to first subscribe to my YouTube channel, and you share, you like, and comment in case of anything. So very many different factors affect the rate of chemical reaction, and you realize that these factors are the ones that determine how fast the reaction is or how slow this reaction is. There are very many, but amongst them, we shall cover concentration, and as well as concentration of the reactants, in the solution. We are going to cover temperature, we are going to cover pressure. Pressure only affects gaseous, let me say for gaseous reactants. Then we shall look at particle size. We've got particle size, or what we can call the surface area. And this is specifically for solid reactants. Then we have catalysts. Then we've got light intensity for photochemical electrons. Light intensity. So you find this one common in photochemical reactions. But we're going to begin with the concentration, and then we see how how concentration affects the rate of a chemical reaction. So let's begin with the concentration without any delay. Concentration. Now, when we talk about concentration, we are trying to look at how close together the solid particles are. How close together the solid particles are in a given solution. Implying that the higher the concentration, all right? The higher the concentration, the faster the reaction. What happens is that increase in concentration of the reactants will increase the number of reacting particles per unit volume. And the moment the number of reacting particles increase, that will increase the chances of collision of the particles. And as these particles collide, they start moving on a high rate. So maybe can say increase in concentration as a general idea, increase in concentration of the reactants let's say increases the rate of reaction. Increases the rate of reaction. Meaning that the decrease, that's the opposite. The decrease decreases the rate of reaction. Why? Because an increase in concentration, the reason is because an increase in concentration increases the number or the total number of reacting particles per unit volume. So when the number of increasing particles per unit volume increases, remember we've said that earlier, we said that concentration is the measure of how close together the solid particles are in the solution. Okay, so it increases the total number of reacting particles per unit volume, full stop. This makes the reacting particles to become closer to each other and thus colliding more frequently. And the increase in the greater number of collisions leads to the greater rate of reaction. So we can say that the greater the number of collisions per unit time, the greater the rate of reaction. So I'm assuming that these are students in a line of food waiting for lunch. Maybe senior sixes are lined up here. In those schools where students draw lines or make lines to the kitchen. And then as you're there standing, they bring senior ones in the same line. The concentration has increased. Maybe you were 70 senior sixes, now they have brought 100 senior ones. The concentration has increased. The number of people involved for food have increased. This one brings you people together, and as you come very close together, you're going to start colliding as you push. As you push, it means the second person pushed the first one. The pushing will start from behind until the first person is pushed. So the greater the number of those collisions, the speed, the more or the higher the speed to reach the source of food. So here, increase in concentration, reactants increase the rate of reaction, that is a mark. Then you have to tell me that increase, because an increase in concentration increases the total number of reacting particles, that is a mark per unit volume. This makes the particles to become closer to each other and collide more frequently. The greater the number of collisions, the greater the rate of reaction. Those are roughly 2 marks when explaining. So we are going to see how the effect, we are going to look at the effect of concentration. So I'm going to give an example of something to think about. Let's see. Example. The rate, let's say the rate equation for 2A must be giving us C is given by rate is equals to, okay, concentration of A, concentration of B squared. How will the rate of reaction alter if concentration of Roman 1 A is doubled but concentration of B is kept constant. Two, concentration of B is halved but concentration of A is kept constant. Roman 3, both concentrations of A and B are doubled. So, want to see the effect of altering the concentration. So we are given the equation 2A plus B going to C, and we are given the rate equation as this. They want us to tell if we double A and keep B constant, what happens? So we are going to solve this by calculation. For Roman 1, remember, your given rate as equal to K times concentration of A times concentration of B squared. So if they double A and keep B constant, what does it mean? It means that our rate is going to be K. They have doubled A, so it is twice A, but kept B constant, so it will keep B then squared. So this is going to be, now we want to see how has the rate equation been affected after bringing in a new term. So we have to make sure that we factorize so that we see by how many or by what factor has the rate equation changed or has the rate changed. So if we put out 2, it will be 2K, then A, B squared, implying that this is what you had originally. So this is what you had originally before involving a 2. So it is twice the original. So we shall say that, we shall conclude and say that the new rate is twice the initial rate. As simple as that. Then for Roman 2, they're saying concentration of B is halved, but the one of A kept constant. So still we shall say rate is equals to K into A, then B squared. That is what you have initially. So they are having, concentration of B is halved. So we shall have K, this will be A, because A was kept constant, then B will be a half, B, then squared. So this is the same as K, A, this square affects a half and affects a B. So one can have B squared separate and then a half squared also separate, because it is the concentration of B was halved. So it means we have a half B, but the whole of the thing is square, meaning this square affects this and this. That's why I've moved it out. So that I keep with the original and what by what figure or by what factor has it changed. So this is the same as, this is a quarter, K, concentration of A, concentration of B squared, implying that it has changed by a quarter. So you don't need to put this. I'm just showing you that this is what we initially have, and this is the factor that has been introduced. So therefore, you'll conclude and say, new rate is a quarter times the initial rate. Then the last part, both concentrations of A and B are doubled. So for 3, when they double concentrations of A and B, we shall have rate is equals to K times concentration of A times concentration of B squared. So if they double both, mean that we shall have K 2A times 2B. They are doubling both. So it is going to be, here we pull out a 2, so it will be 2K concentration of A. This 2 will square this, so it will be B squared and 4 times 4. So this 402 will multiply to make it 8. We shall have 8K concentration of A, concentration of B squared, implying that the new rate is 8 times the initial rate. Right? So we are going to do another case, and we see how we're going to do another case and then see. Another question. The rate equation. Let me see how to bring it down. The rate equation. Reaction between X, Y, and Z is given by rate is equals to K X squared Y Z. State how the rate of reaction, would change if Roman 1 concentration of X is doubled while concentrations of Y and Z is kept constant. So I will do one by one as I do the solutions. So we are saying that the concentration of X is doubled. It implies that rate is going to be equal to K. We are doubling X, so it will be 2X. It's going to be 2x, y, and z. Now, of course, here you can see that this will be 4. It will multiply here. It becomes 4. You pull it out. So it is going to be 4k x squared y z. What does it mean? This is what you have initially. So it has quadrupled. So the rate of reaction quadruples, or is 4 times the initial rate. So you can say new rate is 4 times the initial rate. The new rate is 4 times the initial rate. Or you can say that the rate of reaction quadruples. One can say rate of reaction quadruples. See if that is okay. 2, let's see what happens when all concentration of all the reactants are halved. Concentrations of all the reactants are halved. So when you have the concentrations of all the reactants, we shall have rate is equals to, we'll be substituting in this rate equation. So is equals to K, concentration of X is halved, so have a half X squared. We have a half Y, and we have a half Z. So this is going to be a quarter times a half times a half. So that is going to be 1/16 outside. Then K, X squared, Y, and Z. So this is the initial. So it is decreasing by 16. O is 1/16 times the initial. Here, you need to know that the moment you say a half X then squared, this square affects a half and affects X. So it will keep X squared, but then this is a quarter. After squaring, this is a quarter times a half, that is 1/8 times another half, that is 1/16, which I've moved out. So you can say, the rate of reaction, new rate, is 1/16 times the initial rate. It's 1/16 times the initial rate. That is what you need to do. Or decreases by 16 times. It decreases by 16 times, but all these conclusions are okay. Then another fact is, let's see, when X is kept constant, -3, if you keep concentration of X constant, concentration of X is kept constant, and or while both concentrations of Y and Z are trebled. Now, from the other rate equation, which we have as rate is equals to K times X squared, Y, then Z. We are going to have that when we treble, this one is kept constant, so it will be rate is equals to K, X squared, then you're trebling this. Trebling means 3 times. So it is going to be 3 concentration of Y times 3 concentration of Z. So this is the same as K X squared times 3 concentration of Y times 3 concentration of Z. So this is 9. Right? So it's going to be 9 kx squared y z, implying that the initial, rather the new rate, is 9 times the initial. So we shall say new rate is 9 times the initial rate. 9 times the initial rate. Then Roman 4, concentration of X is halved. Then that of Y doubled and Z kept constant. If that's the case, still first write the general equation, rate equation, okay, x squared y z. Concentration of X is halved, so it is going to be K. You're halving the concentration of X, so it is K times a half concentration of X. Everything is halved, but square. So this should be the same thing. Or one can write it as a half X, then everything is squared. Still it works. So then 1 of Y is doubled, so we shall have 2Y, and then Z kept constant. So it is going to be a quarter outside. Let me put a quarter K X squared. Why a quarter K? Because this half is, this square will square half. Then times that 2, you can move it out, concentration of Y, then times Z. So this 2 will reduce this 4, so we shall have a half outside. A half K X squared Y Z, implying that the new rate is a half times the initial, or the initial decreases by 2, or is halved. Okay, so one can say the rate of reaction, or the initial rate of reaction, the rate of reaction is halved. And say is halved, one can say the rate of reaction decreases by 2. The rate of reaction decreases by 2. One can say the rate of reaction is a half. The new rate is a half times the initial. So all those reductions can work. So I want to give you an assignment for you to do, a question to do here. All viewers, I'm giving a question to do, and we shall confirm that this is understood. Then in our next videos, we are going to report other factors of temperature, catalyst, surface area, and pressure. So let's look, let me leave you with the assignment to do. Assignment to all viewers. The rate of a certain reaction is Using the rate equation. If certain reaction is R is equals to rate is equals to K, concentration of A, B squared then times C. State how the rate of reaction would change if you need to note that these square brackets represent concentration. If Roman 1, B, and C were kept constant, and A was doubled, 2, A and C were kept constant, and B was halved, Roman 3, A and C were kept constant, and then B doubled. Finally, A, B, and C were doubled. Let me add A, B, and C were halved. Maybe VI, A, B, and C were trebled. So that is the exercise to all viewers about this effect of concentration. See you in another video as we record temperature and catalyst. See you.